then you find miracles. And each of them that I'm going to talk about, you can think of a PhD project that you might give to your student. One is optimizing solar panel performance, and you can do the real-time monitoring over here. Here, the AI power system occasionally and continuously should monitor solar panel performance, detect inefficiencies, and identify issues such as dirt accumulation, shading, or hardware degradation. Examples could be AI algorithms can analyze the data from sensors and IoT devices so that you can get optimal energy generation. Then you can think in terms of predictive maintenance. Again, in that area that I'm talking about, optimization, you can look at predictive maintenance, where you can use the AI modules to predict equipment failures and recommend proactive maintenance schedules, minimizing the downtime and reducing repair costs. An example could be neural network analysis, historical performance data to forecast potential failures in inverters or panels. Then the third one in optimization you can look at is solar tracking system, where you can use the artificial intelligence to optimize the orientation of solar panels to maximize your solar sunlight capture throughout the day. Example could be machine learning algorithm, which you can adjust the angle of panel based on weather conditions and real-time solar radiation data. So that could be three on optimization. The other one on energy production, let me talk about the first one that I think of is AI modules, which you can analyze weather pattern, satellite imagery, and historical data, so you can accurately predict the solar energy generation. You can enhance the grid stability. You can enhance the grid stability by aligning energy production with demand, and this can help solar farm operators, especially plan the energy storage and distribution effectively. Here, the example could be deep learning algorithm process. The third thing that you can do is grid integration, and the best example is smart grid, where you can use AI to optimize the integration of solar energy. This is a big problem because there you can balance your supply and demand dynamically. So if you can use reinforcement learning algorithms, they can manage your grid load and prevent overloading and blackouts. The second type you can do is energy storage optimization. AI can improve battery performance by predicting charge-discharge cycle and minimizing energy losses. Here, the example that I can think of is using artificial intelligence so that you can maximize or ensure the efficient use of your energy system, like the lithium-ion batteries in solar farms. The third type could be the demand response management, where the AI management enabled system can analyze the consumption pattern, so it can analyze the solar energy production with user need. The example can be you can devise a smart home which has got all the powering is done through the AI adjustment of the energy usage depending on the solar panel availability, reducing reliance on the grid. The fourth group of projects that you can think of is actually selecting a site where you can do the AI, use the AI to analyze the geographical, meteorological, and environmental data so you can identify the optimal location for solar farm. And here, the example could be AI-powered GIS tools so they can evaluate factors like solar irradiance, land costs, and proximity to the grid. The second thing could be design and configuration, where you can use AI to assist in designing solar farm by optimizing panel placement, spacing, and orientation for maximum efficiency. Here, the example could be genetic algorithms and simulate thousands of design configuration to identify the most efficient layout. The other type is the fault detection and analysis type, where you can use AI system to identify and classify faults in solar farm, such as broken panel or wiring issues. An example could be using computer vision algorithms to analyze drone or satellite imagery to detect panel damages. And the fifth group is using AI in residential solar system, where you can have a personalized recommendation using AI tools to recommend tailored solutions to homeowners based on their energy usage, budget, and location. Here, the example could be AI-driven apps which could power the detailed cost-benefit analysis for adapting rooftop solar system. And the last type on that AI residential system is energy efficiency and improvement, where you can use AI-enabled smart home system, where you can optimize solar power, so you can ensure appliances run during peak solar hours. Example could be in virtual assistant integrated solar energy management with home automation system. The sixth type is the advancing solar energy research. AI accelerates solar energy R&D by simulating material property and identifying new PV material. Here you can use a deep learning model to predict the efficiency of novel materials like perovskite, reducing the time and cost of experimentation. And the last type is promoting the accessibility and adoption. AI can simplify the financing and adopting of solar energy by assessing creditworthiness and offering microfinancing options. Here, the example could be an AI-driven platform like pay-as-you-go type of solar solution using machine learning, so you can predict how you can do the payment, especially in areas where there's a lot of challenge collecting the payments. Now, AI integration challenges are there. The challenge is there in the data availability and quality. That means the high quality real-time data is definitely essential. If you want to train your accurate AI model, that is one challenge. The cost of implementation is definitely the second challenge, because AI requires initial hardware, software, and expertise investment. Cybersecurity is definitely a challenge. It's a great challenge nowadays. Everyone is talking about this, because once we are talking about AI-powered solar system, which is connected to the grid or IoT devices, they are vulnerable to hacking and cyber attacks. So, and the regulatory barriers are definitely there. Every time I talk to people, especially when I'm doing consulting work, there's always the regulatory work when the policies for AI and renewable energy are still evolving, and the policymakers are not aware of it. Now, some of the future potential and conclusion that I have is look at autonomous solar power. Let me fully automated solar farm managed by AI systems. If you have that, you can revolutionize your energy production and reduce your operational cost. The other potential could be in energy trading platform. You can use AI that can facilitate peer-to-peer solar energy trading. So household can buy and sell power to the others. So everyone becomes a prosumer, which is not only consuming electricity, but also producing electricity. Then you can think in terms of AI-driven innovation. If you keep on adding all the advancement that I talked to you about, there will be going to be more breakthrough in solar panel design, energy storage, and distribution. AI is a game changer, my friends. And in the solar energy industry, this is definitely going to play a very big part. It will drive the improvements in efficiency, reliability, and accessibility. My friends, AI is helping accelerate the transition to clean energy future by addressing key challenges in solar energy generation, storage, and distribution. And my friends, as AI technologies advances, their integration with solar energy system promises to unlock new opportunities for innovation and sustainability. Now, this other space-based solar power. Many people ask me this question, Professor Kalam, what is this space-based power? I tell you, SBSP, which is space-based solar power, is an innovative approach to harness solar energy directly in space and transmitting it to Earth. So you bypass the limitation of ground-based solar system. It has the potential to provide continuous, large-scale, and clean energy. And let us look at this. How does it work? You do the collection by using satellite, which is equipped with large solar panel, which captures solar energy in space, where sunlight is uninterrupted by atmospheric interferences or clouds or night cycle. So there's no problem. 24 hours, you've got energy. Energy conversion. The captured solar energy is converted into microwave or laser beam for transmission. The other thing is energy transmission. Energy is beamed down to receiving station, which is antennas on Earth, and the energy distribution, the energy which you have collected in the ground station is converted into electricity and integrated into the grid. The advantage of SBSP is that you've got uninterrupted power. 24/7 you've got power. Okay, you've got no issue, a problem. efficiency is high. You can have solar energy which is collected in space, which is much more better. You have avoided all these problems of having the atmospheric scattering and absorption. You do not have problems of land usage. Because everything is done in space. SBSP eliminates the need for large solar farm on Earth. We are using whole farm nowadays. Instead of growing our vegetables and other things, we find that we are just putting solar panels over there, and we are unutilizing the full capacity of the land, which can be done for that purpose, for agriculture, conservation, and habitation. Scalability, multiple satellites can be deployed so that you can meet the energy demands. The global energy access, beaming energy to remote or underdeveloped regions, provides clean power without requiring grid infrastructure. So you don't need, you can get that all that energy somewhere else and supply it to, say, in the remotest part of Africa. The environmental benefit of the SBSP is that it's a zero emission energy source. So there is no dependence on solar fuel on fossil fuel, and helping combat climate change. But the challenge is cost. Definitely the cost is high. Launching satellite, manufacturing large solar panel, and building ground infrastructure investment is significant. Energy transmission losses could be there because you want to convert the energy to microwave or lasers and back into electricity. There might be energy losses. Safety concern. Now, this was one of the things when we were looking at it in analysis when I was a student at that time, when they said that if we are going to beam energy and if the flight comes in between, you might burn the whole aeroplane. Now, that could be a concern, but there is a solution. That's a different thing. I don't want to talk about it, but beam energy must be carefully managed so that you can avoid harm to humans, wildlife, and the environment. Technical hurdles could be there. In order to develop lightweight, efficient solar panel and renewable energy transmission technologies, there's a huge amount of challenges. Materials are required. New types of technologies are required. Satellite must be able to withstand extreme space conditions, including radiation and meteoroid impacts. Then regulatory and geopolitical issues are there. The coordinating global regulation for energy transmission and reducing concern about the dual usage of space technology, especially for military application. The most recent advantages are there in modular satellite design, where you can be assembled in space, reduce the need for massive rocket launches. You can use for efficient transmission by using microwave beam technology, very well advanced, using laser beam transmission, which can use for improving your energy transfer efficiency. Use lightweight material. More materials are coming, but with the coming of ultralight and flexible solar panels, this will reduce your payload weight and lower the launching cost. Space elevator concept, though speculative, you might find that we might get space elevators coming in, and if that comes in, that's definitely going to reduce the cost of transporting such materials into orbit. Now, the application that is there is a global energy supply. SBSP can supply clean energy to densely populated urban areas, rural areas, industrial regions. You can do disaster relief, the power disaster is stricken or remote area where infrastructure is damaged or non-existent. You can use it for military strategic use. SBSP can power military operations in remote locations. And you can for space exploration, that is space-based solar power system can supply lunar bases, Mars colony, or deep space missions. The future outlook, I think, is going to be the one that I'm seeing is going on in Japan, which is done by JAXA, the Japan Space Agency, which is actually developing microwave-based, solar-based solar power system, and energy transmission has been successfully done. China, by 2030, plans to build a space solar power station capable of beaming energy to Earth. NASA in the United States has explored SBSP concept like SPS Alpha, which is sort of satellite. European initiative is there. Space Agency has launched to evaluate the flexibility of space-based solar power. Now, key milestone needed is the cost reduction. We have to reduce cost in launching reduction through reusable pockets. The technology maturity especially developing efficient, scalable, and space energy transmission system. You can't do it alone, my friend. You have to have collaboration. International collaboration is that will also start regulatory framework, cooperative agreements for equitable access and deployment. So remember, there's going to be a lot of investment, and only investment from the government will not be enough. You need public and private investment. In funding from government and private company can accelerate R&D and pilot projects. So I believe that SB represents a revolutionary step towards sustainable energy solutions, offering the promises of limitless clean energy for Earth and beyond. While there is significant technical, economic, and political challenges remain, ongoing advancement in space technology and international collaboration bring SPSB together into reality and make it a cornerstone of the future global energy mix. For developing countries like India, okay, there is energy poverty. More than 700 million people globally have got energy problems. So we have to use our essential items. Everyone should have banking, eating, communication, about healthcare. Solar energy does offer a transformative solution. It gives you clean, reliable, sustainable power supply across the remote areas. But the breakthrough is because solar energy is in abundance. You can use it in decentralized system. It is affordable. Then you can use it in off-grid home system. You can use it as solar mini grid type. You can use it in solar power applications. And I've given all the examples, portable solar solutions. Then there are economic advantages, especially in health improvement, or educational opportunities are there, economic empowerment is there, gender equality is there, environmental sustainability is there. But there are challenges is the cost. And then it's technical and maintenance issues with the awareness and acceptance is a problem. People are not aware of all the policies are there. And this is definitely, policies are always along with finance. So you have to have a strategy, and the strategy is to have some sort of finance modeling. You have to make sure that your workforce is there, so you have to do proper training and capacity building. Public-private partnerships. Then the policy and regulatory support is required, as well as innovation and technology. So some of the success story has been in East Africa. In East Africa, the NCOPA Solar has done a pay-as-you-go scheme solar initiative. This is giving affordable solar system to over 1.5 million households in Kenya, Uganda, and Tanzania. Then in India, there is very good example of solar-powered schools. Solar power panels installed in rural school power classroom, providing internet access and enhancing education to the primary and the secondary school. In Bangladesh, Grameen Shakti is a very good example where the organization installed millions of solar systems transforming rural energy across access, giving them access and livelihood. So solar energy can definitely eliminate energy power in developing regions by providing clean, affordable, and reliable power. Solar energy can empower communities, boost economies, and create a sustainable future by addressing challenges like finance, technical expertise, and policy gaps. With global collaboration and investment, solar technology can be a cornerstone in the fight against energy poverty. Now, my challenges and future outlook, very important, intermittency and reliability. You are not at all dependent on weather. Grid integration is definitely an issue. Energy storage limit, high cost is there because of lithium ion and solid state batteries. They're very expensive. Limited capacities are there, especially the current technologies cannot meet the demand 24/7. Land use is definitely a problem, whether we should use it for agriculture purpose or for solar farm. Okay, there's definitely there's a conflict over there. Material sourcing is an issue. Mining materials, especially you are finding today that the problem that the United States is having procuring rare earth material. Most of the equipment that you use in your mobile phones and all your electronic gadgets, which uses rare earth material, and that is only with certain countries in the world they have that. So that might be a big issue for your SBSP. Then recycling, that's a very big problem. recycling and waste management. People do not understand, but we have been using it for 30, 40 years in Australia. We have got a big problem. What happens when the light panels end the end of the life? Because this is a huge problem. How we are going to solve this? There's going to be a lot of toxic material, especially silicon, that will come out. What are we going to do with it? Then initial cost and financing, especially the upfront cost that I talked to you about, especially the one that is installation and storage, and that can deter adoption. Financing gap is there. I know that many countries have adopted 1/3 by the government, 1/3 by the utilities, and 1/3 by people. That is possible. That would be good. But if that is not the initiative of the government, is not there, and the utilities are not there, then you find it very difficult to have this fully implementable. Policy is definitely there. The government has got inconsistent policies. You can find that this can disrupt your energy project. Grid parity is required. This is not cost competitive with fossil fuel, particularly when there is subsidies which are there for the non-renewable energy sources, but there are no subsidies for the renewable energy sources. The future and outlook that I can think is material is one of the things that this is technology part, where we can look at perovskite, quantum dots, and other photovoltaic material. Advanced type of storage solution, the solid flow batteries will definitely improve the reliability and affordability. Integration is an issue. Then that can be solved by using AI and IoT. You can have a smart energy system. Okay, microgrids will enhance your energy access in remote and off-grid areas, and decentralization of energy system, that is residential and community sector, especially the distributed solar system, will empower individual and the community to generate the energy. I told you, we will no longer be the consumer, we will become the consumer. We will be producing energy and selling it to your neighbors. Peer-to-peer energy trading, where blockchain and smart contracts could facilitate energy trading between houses and surplus power. Scaling up development, utility scale solar can combine with the enhanced grid infrastructure. There will be large-scale solar power farm will support the transition to renewable energy dominance. Hybrid system, where you can pair with solution with other things like wind, hydro, and storage solution. The circular economy, a lot of people are talking about this at the moment, especially what to do with the recycling of panel, then whether this material that we have got is sustainable, because we have to come up with eco-friendly material so we can have minimum environmental footprint on solar production. Global collaboration is definitely required. That'll give you the harmonization of policy when there'll be international agreement and consistent policy, and therefore solar will be adopted worldwide. Financial support is required, as I mentioned, because you have to have increased investment in solar projects, especially developed countries. And if that happens, then this can bridge the energy excess gap and spur economic growth. So while solar energy faces challenges, its future is bright with technological advancement, improved integration with energy systems, and a growing global commitment to renewable energy. Overcoming these obstacles will require collaboration amongst governments, industry, and research institutions, and sustained investment in innovation and infrastructure. Solar energy has the potential to be a cornerstone for sustainable and renewable. So I think I'll stop at that and ask if there are any questions from the audience. I think I'll stop there and ask questions if there are any. Any question?
Participants, do you have any question? You can write in the chat box, or you can unmute your mic and ask, sir. Sir will be happy to answer your queries.
Yeah, I'll try to answer. I'm not saying I will answer. I will try to answer.
Sir, one message in the chat box. Momita Ghosh, she is telling that The all things has been explained properly, so no question.
Oh, thank you very much. It's very nice. That'll give me some time to sleep now.
Nice explanation.
Thank you very much, Professor Muthukumar. Thank you very much, Professor Muthukumar.
Thank you, sir, for giving us your time. We are very much obliged to you for giving us this session. Thank you, sir. From our side, there is a small token of appreciation for you. Please accept this, and please let me know if you see the screen, if the screen is visible.
Yes,
to
I
you.
can see it. I can see it. Professor, I can definitely see it. Thank you very much. That looks very nice.
Please appreciate this token of appreciation from our side. Thank you, sir.
That's very
And
good.
we hope that we will get you with us and you will give a nice session in future also. Thank you, sir.
Definitely, definitely. It'd be a pleasure. I'm from Kolkata, just for your information, if you don't know me. I'm from Kolkata. So, and Durgapur, I come normally. I come to, and I do a lot of work for NIT, and therefore, it wouldn't be a bad idea to come and visit your SVSD at some time, if there is requirement.
Yes, sir.
Okay.
Yes, sir.
And
Yes,
thank you very much. Namaskar to everyone, and Joy Bangla, as we say. Bye bye.
Bye, sir. Bye, sir.
Bye bye. Bye bye.
Bye, sir. Take care, sir. Participants, please stay with us. Our next session will start from 3:30 p.m. and our speaker is Dr. Kollan Chatterjee. He is a professor of IIT Dhanbad. Please stay with us until 3:30 p.m. Okay, sir. Can you make it slideshow mode?
Is it visible?
Yes, sir. It is visible. Sir?
Yes.
We are going to start.
Yes, ma'am. I'm going to
Just
start.
we will take some seconds from you. Good evening, everyone. This is our last session of this 6 days Otol FDP, and we have among us Mr. Joydev Odok. He is a super divisional engineer from DVC, Kolkata. Sir, with your permission, I would like to read out your biography to our participants.
Okay.
It's my pleasure to introduce Mr. Joydev Odok, Senior Divisional Engineer Electrical at Damodar Valley Corporation, Kolkata. With over 20 years of rich experience, with over 12 years of rich experience in power system operation, maintenance, and project management, he has played a key role in advancing DVC's electrical infrastructure. And alums of IIEST Sipur, Mr. Odok has specialized expertise in switchyard and substation operations, transformer maintenance, testing and commissioning of electrical equipment. His innovative approach and technical excellence have earned him several recognitions, which include Best Employee Award in 2022 and Special Appreciation in 2024 for outstanding contributions to system improvement. He has also presented his research at premium institute like IISc Bangalore, IIT Bombay, and twice secured the best or the first position in DVC's ideation contest. His dedication, leadership, and innovation truly reflect his commitment to sustainable power development and operational excellence. From the organizing team, I would like to thank you, sir, for being with us and giving us your time and taking this session. Thank you, sir. The
Thank
session
you, madam, for this opportunity. Now may I start my session?
Sir, can you make this screen full screen in slideshow mode?
Yes.
In slideshow, yeah.
Is it okay?
Yes, it's okay, sir. Okay, sir, you can continue, sir.
Okay. Good evening, everybody. And today's topic, based on the supply reliability and enhance reliability and prevention of electrical system, I will discuss this topic based on the insights from practical case studies. Okay. So overview of our topic for today's session, that is introduction of the reliability and insights of case studies and importance and key definitions. Then we will go to the key causes of electrical tripping and supply failure. Then what are the reliability indicator based on which we can consider whether the reliable system is reliable or not, and the matrices. Then we will go for the different types of case studies, with the DVC case studies and outside DVC case studies. So after that, we will go the conclusion and strategies, best practices from above case studies, and then what recommendations should be there in power plants. Power plant and utilities. There are different types of utilities, that is the transmission utilities, distribution utilities, and generation utilities, and also the industrial, household, and commercial consumers. So then we'll go for summary, and then lastly we'll go in question and answer session. So first, for the utilities, we know the utilities type, that is mainly three types of utilities: generation, transmission, and distribution. So for the distribution, there are several type of consumer. They are maybe distribution or generation, etc. The consumer may be radial, based on radial feeder, that is the retail consumer, or bilateral consumer. So for all type of utilities, three things are important for that is sustainability, reliability, and efficiency for any utility, whether it is generation utility, generator utilities, or transmission or distribution. So first we have to sustain, then we have to provide reliable services, then we have to improve our efficiency. So now coming to the introduction and importance, why reliability matters. First, electrical system from the backbone of the industrial, commercial, and utility operations. Reliable power ensures uninterrupted supplies. So that is the reliability, means uninterrupted continuous supply to the consumers without hampering their interruption, their supply. And for that, what we require, that is the supply that we supply from the substation, or for bilateral consumer, there are for generating station, that should be uninterrupted, and maintaining the quality of the supply. The quality of the supply depends on three things mainly. First one is the voltage, second one is the frequency, and third one is the power factor and harmonics. That main three things, that is the voltage side should not be there, and quality there be, frequency should be maintained, and other weather condition or other conditions should also be not there. That is the fundamental frequency should only be there. without any harmonics. So importance of power supply reliability. It ensures continuous operation, reduces downtime, and avoids unexpected shutdown of critical loads, improves safety, protects equipment, reduces operational cost, and enhances power quality. For any industry, whether suppose you can consider your household supply also, household, commercial or industrial. When the supply interrupts, then the production of any industry or the facility of the hospital or emergency services that gets hampered. And that's for the industry, if the interruption occurs frequently, then the production hampered, then the efficiency gets down and they faces losses. They can't sustain. Sustainable is not possible for them. If such type of, that is operational cost also increased, and protect equipment. If several times number of times of interruption occurs, then the equipment goes to frequent failure. Enhances power quality. If reliability is being maintained, then power quality will be there. That is the voltage, stable voltage, frequency, ensure efficient equipment performance. Also, if reliability is there, then business productivity, that is the production of material, or commercial aspect also matters. So regularity compliance also implemented, that is the SAIDI, SAIFI, KAIDI, etc. That is the reliability indicators. That also that is the regulatory compliance required for the value of SAIDI, SAIFI, KAIDI, etc. That also to be maintained. So reliability matters. That is the first thing, is the safety risk. So if there is no reliability, that is the tripping or downtime increases, then the safety risk is there. For any thermal power plant or any substation, if the tripping occurs frequently, then that leads to the bursting of equipment or failure of equipment, which causes the failure of safety protocols. And also operational interruption also occurred, and that both those things leads to financial losses. How reliability is defined? Already I have told, that is the availability, continuity, that is the continuous availability of the power system, power supply, continuity, continual supply without any interruption, and quality, that is the voltage, frequency or waveform, that is the without harmonics free, that is the shall be within acceptable limits. So type of electrical tripping, if we consider the practical conditions, there are different types of electrical tripping that may be overload due to the overcurrent draw by the drives used by the consumer or by our itself in our plant. So overload tripping may occur. Overcurrent earth fault, that is the fault condition. If any earth fault or overcurrent occurs, that is the phase-to-phase overcurrent, phase-to-phase, and earth fault may also occur. Under voltage, over voltage tripping.
Sir, your voice is not coming. I think an internet issue is there, sir.
High current for any drive, motor, etc. The primary initial current, starting current is much more than the normal full load current. Another is tripping in the protection device operation, that is the MCCB relays, and mainly the circuit breaker. So protection device, when protection device operates through relay, it operates through relay normally. And after getting operation of relay sends command to the circuit breaker or MCB or MCCB, wherever it applicable. equipment or system faults. Second, next one is the equipment failure, differential or distance protection tripping, LBB, local breaker backup tripping. This is this type of tripping, that is the differential distance protection, and LBB, bus differential tripping. These are applicable only in switchgear. Local breaker backup protection, it is when the system is 132 kV and above, then we use LBB, and differential protection 220 above and above, we use differential and LBB both. LBB and differential protection, bus differential protection, this is the vital and complex, the main protection of switchgear. That these protection, if this protection can lead to the total power failure of the system, complete failure of the system. That is occurred in the DVC also sometimes. A total power failure, 1 unit, 2 unit, and 6 unit at a time trips through this protection. Transformer differential and all other type of tripping, that is occurred based on the equipment. Equipment wise, there are different types of tripping also there. So key definition first, power reliability, that is the reliability, the system should be reliable, and power reliability, power quality, that I'll already discussed. Electrical system tripping due to different fault reason, fault or overdrawal. So that is the electrical system tripping. Protection coordination. Protection coordination is the ensuring effective device operate in correct sequence. Suppose coordination means, suppose there are circuit breaker in upstream and downstream of a line. So for a substation, if it supplies power to the consumer, there two breaker will be there. One breaker at substation end and one breaker will be at consumer end. So protection coordination should be in such a way, if fault occur at the downstream of the consumer end, then the consumer breaker should only trip, and after that, if it fails to trip, then only upstream breaker, that is the substation end breaker, should trip. Otherwise, if coordination is not proper, protection coordination or relay coordination, then the upstream breaker will trip first, then it will trip, it will make total power failure of the consumer end. So this coordination is vital for reliability point of view. And next one is the maintenance practice. That is the preventive and predictive maintenance. Preventive maintenance is scheduled, and predictive maintenance is based on the condition monitoring and continuous monitoring. We can predict that this maintenance is required. And preventive is the schedule. It is fixed schedule basis. For system trips, system tripping is the different reason, that is overloading, short circuit, earth fault, insulation breakdown, poor protection coordination, equipment degradation, harmonics, and power quality issues. Different type of. There is the same similar different common causes of electrical tripping. Now, if we consider for the different type of fault, this is the schematic of a thermal power plant. I'm starting from the coal handling plant to the transmission line, that is the switchyard. Last one is this one. This one is the transformer, and this is the coal handling plant. So here the several equipments are there. So from coal handling plant to boiler, and boiler it evaporates the water, and that water goes to the turbine and rotates turbine, and this turbine works as a prime mover for this generator. This is the generator, and generator based on the turbine and the excitation from external sources, DC sources. This generator for thermal power plant, it is an alternator. It is called turbo generator or alternator. So this generates supply, and this supply goes to the transformer. That is, this transformer is called generator transformer. So one thing keep in mind, for any generating station, this transformer and generator, normally there are no switching devices in on-load condition, because this generator, for 210 megawatt generator, we use the voltage level of 15.75 kV, and for 250 megawatt we use 16.5 kV. And for 500 megawatt, we will use 21 kV at generator end. Then we step up that voltage from that kV to the transmission level through this generator transformer. So here one question is why this is done in power system. Why generator voltage is not increased at this level? That is transformer, that is generator transformer cost around 20 to 30 crore for a 210 megawatt. So why, and maintenance cost also there. Can anyone say that why this voltage is used at low voltage level? Then we are using transmission generator transformer. They, in spite of using this cost of generator transformer.
Any response from the participants?
Anyone from participant? Why we are using this generator transformer to step up? Suppose the generator voltage is 16.5 kV, and we are stepping up this voltage to 220 kV, 16.5 through this generator transformer, and this generator transformer itself a costly, that is 20 to 30 crore, and its maintenance cost also heavier. So in spite of that, why are using this generator transformer? We can use, produce voltage at generator level, that is 220 kV or 132 kV, and we can transmit to the direct switcher to the transmission through transmission line. Anyone from participant can tell that why we are using this system, that is generator, and we are usually using generator transformer without any switching device between generator transformer. So in spite of that, we are not using any switching device between generator transformer and generator.
Any response from the participants? If not, then I am going to answer it.
Okay.
Sir, if you step up the voltage, then it will decrease the transmission and distribution loss. But
Yes.
if we want to generate this high voltage, then there will be an insulation problem in the alternator.
Yes.
The alternator, inside the alternator, it will be difficult for the wiring. If we cannot give so good
Yes.
insulation system inside the alternator wiring, it's not possible for the rotor or stator. It's not possible.
Yes. This is correct. Actually, insulation program. Actually, we have the insulation level. That is, we can memorize the insulation level. You are rating bread for her or his comfort. YEA, U, Y for U, A for R, A for YA, that is 90, 105 degree temperature. First, Y is 90 degree temperature, insulation. And you are eating bread, B for F, R, H, and C. So this is the insulation level available with us. For generator, we are using B or F type of insulation class. So if we actually there is a problem for cooling of generator, here we can use only two types of cooling medium. One is hydrogen and another is water. We can't use any insulating oil there.
Sir,
So,
sorry to interrupt you. Your screen is again in half. Please, full screen is it. Slideshow mode.
now it is okay.
No, sir. It's not in slideshow mode. It is in PPT mode. Now it's okay.
Now it is okay, na?
Yes, sir.
Yes.
Yes, sir.
Oh, that's why as the insulation problem is there, and in case of generator, we can use the cooling medium as hydrogen or water. So that's why insulation problem is there. if we increase the insulation based on the hydrogen or water cooling, then the size of the generator will be bulky, huge. That cannot be transferable from one place to that's a handling problem. These two problems, that is handling and insulation problem, are binding us to keep the voltage in certain level. So, and in between this, there's a generator that's, and we have to transmit the voltage level in high voltage level to minimize the I square loss. And as the voltage is lower in between generator transformer and generator, so the current level is very high in the range of kiloampere. So that's why on-load switching device is not using in between generator transformer and generator. So this is the, so after generator transformer, there are switching devices. Generator transformer, to it goes to the switchyard. After enters to the switchyard through different conductors. Type of conductors are there. Switchyard. This is the sample of switching equipment. This is the isolator. This is the current transformer. This is the isolator, and this is the circuit breaker. And this is also the isolator. Based on the substation types of schemes of substation, whether it may be single main bus scheme, whether it may be 2 main and 1 transformer bus scheme, whether it may be single main and 1 transformer bus scheme, whether it may 1.5 breaker scheme. Based on the scheme, there will be switching equipment. And bay is called the set of equipment utilized for any power from source to destination. This is the way. Now, after that, we have to identify the fault in the system. This is the basic relay system, where after causing any fault in the system, so how we will detect? This is the basic drawing. This is the bus bar, and this is the supplying power to the consumer here. So current transformer is placed here, and circuit breaker is placed here. And this is the basic relay circuit. After the current transformer and potential transformer are the instrument transformer, which replicates the physical system, just replicate the physical system to the relay. So suppose in physical system, the feeder is consuming 200 ampere. The current transformer, it steps down to 1 ampere because our equipment, that is the relay or meter, measuring meter, are designed for low voltage and current, and for actual measuring it multiplies through multiplying factor. So current transformer, for the current transformer, it takes the current, replicate the current of the physical system to relay. If the already setting is already given previously during the commissioning of the system. So this relay, if the current in the feeder gets above the setting value, then it will energize, it will create close the contact. And if this contact gets closed, then this circuit gets energized. If this circuit gets energized, this coil is engaged, connected in the breaker coil. Then breaker, it will pull the breaker, and the contact breaks. And after getting isolated by breaking this breaker contact, fault is there. Considering that fault is there, then faulty part gets isolated. Once faulty part gets isolated, it's not propagated to the bus. Fault, actually, our main aim of the system is to isolate the faulty part only, so that the fault cannot propagate to the upstream zone, so that it can hamper to the other system. So that is our main aim. If potential transformer is used, where voltage is also required for the relay for determination of fault condition. For distance protection relay, for any line, 220 kV, 220 kV, 400 kV lines, there are current transformer and potential transformer, both are required for protection purpose, because a distance protection are based on resistance or reactance method. So based on that, both are required This is the same principle. So this is the sample of a panel of substation. The panel where the relay, this is the relay, and this is the switches. We can operate breaker manually, and this is the different SLD, single line diagram, and this is the transformer, just transformer of the substation used we are using. This is power transformer. So I'm also describing the transformer component so that we can discuss about the what kind of fault may happen that will hamper the reliability of the system. So this is the different part of the transformer. This is the main tank. This one is the main tank. This is the radiator bank for cooling of the transformer oil, and this is the Buchholz relay used between main tank and conservator tank. This is the silica gel breather, and this is the explosion vent. Normally for small transformer we use explosion vent, or for large transformer we use PRV, pressure relief device. So this is the cooling tube. This is the fins, and totally it is called the radiator bank. This one is called radiator bank. So now the common causes of major electrical system, coming to this point, that is overloading and earth fault. This is the main cause. Overloading, that is overcurrent drawal by the consumer, is the main reason. And secondly, the earth fault, that is single line to earth fault. So, and another one is the poor protection coordination. Other frequent contributor includes also insulation failure due to aging problem. That is, if the long aged equipment we are using, we have to test that equipment more frequently than the newly installed devices. For any transformer, if it is new, then we can test in 2 years. But if it is old, more than 30 years, then we have to test in 1 year mandatorily. Different schedule testing is there. So aging problem, and insulation, that due to aging problem leads to the insulation failure of the system, and it attract the moisture also. Loose connection for switchyard equipment or any connection point, the loose connection is the major reason of fault. You can see the tower in the transmission line, the loose point, weakest point of the transmission system is the tower point, where the conductors are connected to through connector from one side to another side. There are insulator and conductor are connected to one side to another side through conductor. So that is the loose point. That's why for during any fault in downstream, the sparking observed inside in nearest area of the towers. The harmonics and power quality disturbance are also present there, and the equipment failure may occur for city. Main equipment failure occurs for 2 types of equipment. First one is the lightning arrestor. Second one is the current transformer. This is the major failure in the substation or any substation or consumer in equipment. And other motor also is there, but for switched equipment or there is 2 types. There is the current transformer and lightning arrestor. So overloading combined with improper protection coordination remains the top root cause. So this is already discussed. So now we'll go for the reliability indicators and matrices. So there are reliable indicators based on the regulator, different reliable indicator based on which we can consider the system, that is the utility, is reliable or not. Suppose DVC is a utility. He is supplying power to consumer. So whether DVC is reliable or not, there is also competitor West Bengal WBSEDCL is supplying power also, and also IPCL is there, CSC is there. So we have to consider whether which system is reliable for any consumer. Then the consumer will approach to that utility. So for that we have to identify and mark the reliability indicators. So first is the SID. Second one is the SIFI. These two are the main reliable indicator for power system. So SID means system average interruption duration index. That is system interruption duration. How much time interruption occurring? So that index is called the SID. So SID is defined as the total duration of the customer interruption. Suppose DVC has or suppose West Bengal WBSCTCL has 30 consumers. Each consumer having 1 minute of interruption. So total interruption for consumer 30 consumer gets as 50 hours, etc. So then total number of consumer is 30. So 50 by 30 is the SID. So total average interruption time, that is the SID. And SIFI is the number of, SIFI is the total system average interruption frequency index. How many times interrupt per consumer on average basis. This is the SIFI. SIFI as a mathematical formula, total number of customer interruption. Suppose there are customer 1 have 5 interruption, customer 2 has 1 interruption, and customer 2 has 3 interruption. The total interruption is 5 plus 1 plus 3 plus. That is the total number of interruption. And total consumer is consumer is 30. So total value we have obtained by this number of consumer is the SIFI. Now MTBF or MTTR. MTBF is the mean time between failures. Between two failure, if there is tripping is already occurring in the system, the time between two failure is the MTBF, mean time between failure. It means how much the one system on utility is available for the consumer. So that is called MTBF, and MTTR is the mean time to repair. So how much time it takes to restore the system? So to between failure and repair, how much time it takes? That means if MTTR is less, then it will be considered as the faster recovery system, as far as it can recover the system from faulty to normal condition. And if MTBF should be greater for reliable system, or MTTR should be less, very less. And next is the THD, voltage unbalance. THD, total harmonic distortion. This is the and voltage unbalance. This is also the reliability factor based on which we can decide whether the power quality of the power from that DISCOM is highly acceptable or not. So for the system, we have to, in ideal condition, the supply should only contain the principal, the fundamental frequency. But that ideal condition is not present in any system. So THD is calculated, and other indicator is the MIFI, momentary average interruption frequency index, ASI, that is the average service availability index, and ASUI, average service unavailability index, and ENS, energy not supplied, and SIFI, modern SIFI enhanced indices, that is advanced form of SIFI, that and SID that account for this also consider for severity, weather condition, and critical loads also. So another one is the KID. KID is the SID by SIFI is the KID, customer average interruption duration index. This is the interpretation for long restoration time, poor restoration performance for high KID, and if it is low KID, then fast restoration and good maintenance and fall response. For example, if there is 120 minutes of SID and 3 interruption is there, so what will be the KID? That is 40 minutes of KID. So now, before going to the recommendation, we'll discuss case studies, different case studies. First, non-DVC case studies. After, we'll discuss DVC case studies. First, this is the common case studies of ASD, adjustable frequency, adjustable speed drives, such as similar to the frequency variable frequency drive (VFD). So they are using they are using these drives and during the transient and capacitor insertion of the capacitor bank, there is the transients occurs, and due to this transient and due to the drive due to the starting of the drives, during that several times the drives getting damaged, or it will costing much. So root cause that is energization transient. So if number of energization increase, then the number of transient will increase. Due to the transient, it affects the equipment all connected to that system. So induce current during startup is much higher. We already know, everyone knows that during if the starting number of starting is increased, then the number of starting current, that is which is higher, much 5 times or 3 times than the full load current. So this will hamper the insulation system of the drives, and it can damage the drives after few operations. So solution, they are modeling with EMTP, electromagnetic transfer transient program. They are transient program, and they are filtering the transient frequencies. So that only fundamental frequency passes through the drives, and it cannot damage the drives. And vacuum switches uses to restrain the switching transients. And outcome of the lesson is the significant. Outcome is the significant reduction in ASD failure reduced, and invest in proper protection switching devices. That benefit always gives benefit. Now case study 2, data center, similar failure was there due to fluctuation, voltage fluctuation, and interruption, harmonic distortion, etc. So after that, harmonic filters applied, and UPS or reliable supply also provided. That's why the problem solved. This is the common. Now coming to the DVC case studies. I'm mainly focusing on switchyard because I have already worked in switchyard. That's why the case studies is based on switchyard. So first we'll discuss about the DC grounding in switchyard. So we know the DC system and AC system for DC system is the heart of protection system. Without DC system, we cannot think of protection system. And why we use DC system in this protection? Because it is independent. For AC system, they are intentionally grounded at the neutral point for start intentionally. But in DC system, they are maybe grounded or maybe ungrounded system DC. So where power plant or everywhere, mostly we use the ungrounded system. So for ungrounded system, ungrounded DC system, the voltage normal DC standard is 220 volt DC. So for ungrounded system, we are utilizing resistor between the positive side to ground and resistance in between negative side to ground. So for an ideal condition, DC voltage shall be plus 110 volt, 110 volt, and minus 110 volt. This is the DC system ideal condition. But in case Mejia and Chandrapura, Mejia thermal power station and Chandrapura thermal power station, these two thermal power station has biggest switchyard in the eastern side. So there in this big switchyard, DC is flowing from one end to another end. There is so much circuit of DC, and due to this long circuit of DC, they are already prevailing in the 2012 to 2015. There was grounding at positive side. The voltage profile was in such a way. This was the voltage profile, initial condition. This is the 0 volt at positive end. This is the positive to ground, and this was the negative to ground. But ideally, it should be the around 50-50. That is, here you are seeing that the voltage is 240. I am already told that ideal condition 220. But for industrial cases, as the circuit is long, so at the charger end or battery end, we maintain 240 and above voltage, so that it there is a voltage drop in the system, different circuit, so that at the end point where we are utilizing protection devices, that is breaker, coil or etc., there it should be above 220 volt. So we maintaining 240 volt plus voltage at the charger or battery level. So this 240 volt, it should be at this level, it should be 120. For 243, it should be 220, 122 and 122. So, but it was prevailing that one grounding was there. So positive to ground was 0 and negative to ground was full volt. Suppose considering that 250 volt. So positive to ground was 0 volt and negative to ground was 250 volt. So during second fault, first fault is existing in DC system. If second fault occurs in the system of bus differential protection, it gets shorted the circuit contact of the bus differential relays, and the bus differential protection operates several times without any relay indication or etc. It creates failure of the total system, and total power failure occurred 2-3 times. So our aim was how to identify this one. Yeah, we have to first make this DC voltage ideal. So for DC voltage, DC grounding checking, the first option was there that the isolating the DC branches one by one and check the whether which branches is faulty. Then isolate the faulty part and normalize the rest. So, but it was not feasible for power station because the power station is not allowing shutdown of any branches. So that's why we have arranged DC earthfall locator. This is the DC earthfall locator. So for DC grounding, for checking of DC grounding, there are normally 3 types of method. First is balance resistance method. This is the balance resistance method where resistance is provided and indicator is provided. 2 indicators. One is in between positive to ground and another is negative to ground. If one gets 0 grounded, then the indication will reflect glow. Indication glow will change. Based on the grounding condition, indicator will change its glow. This is the balance resistance. Second one is the AC signal injection through this method, and another one is the DC signal method. And worldwide, presently for online DC DC fault locator, we are utilizing the AC signal injection, where we are injecting the signal of low voltage and low frequency or pulse type pulse signal. That is around this is the make of browser, and this is the 11 to 12 hertz and sinusoidal 12 hertz and 8.5 to 9.5 voltage RMS. This is a transmitter. This creates the signal, and this signal we are importing this signal to any DC bus, and this receiver are we are connecting this receiver to different branches of the DC circuit. So after that, if any branches are having the faulty part or grounding condition, then this receiver deflects to its highest value. This is the deflection, and there is no deflection. This is the condition that this feeder, DC feeder, this is the 3 DC feeder, and this is the DC bus. So this test subject signal will be injected here. And if ground fault is there, fault is here, then the signal will flow through this path, through ground, and this ground, it will complete its path through this path. Ground and signal, and here signal, and again it flow to the ground. So this signal, this receiver will catch this signal and it will deflect and it will show that fault is there in this feeder. And in the another feeder, this feeder, there is no fault. If there is no fault, then the signal, there will be no signal, this signal, and there will be no deflection in the equipment receiver. So through this one, we identified the DC. To identify the DC, and we have found the fault location and we rectified this condition. After that, we have arranged the DC voltmeter so that this is the partial grounding, partial DC grounding. This is the partial DC grounding, that is the 76 volt is the positive volt and minus 164 is the negative volt. And after that, after rectification, we have arranged this one. So this effect creates the during the faulty condition, there are several times of tripping of units, total unit, that is a loss of crores and above. 1,000 crores losses happened due to the small part of DC grounding. So after that, this is the bus differential scheme. You have to check only this part, that this is the main bus portion and this is the condition. So presently existing condition, there was ground, and if this is the circuit and this is the relay, 96 relay, this is called the bus differential relay. This is called the bus differential. If it operates, then it will this after operation of this relay, it will trip all other breaker in that bus, so that the system gets collapse and it isolates the faulty part. So if grounding occurring at this point, initial grounding and second grounding occurs at this point, then these two paths get shorted and the DC voltage already available here, this will flow to this path and this will energize, and this relay will acting and will create total power failure. Our modification was there, that is the insertion of the actual relay contacts at this point, so that if in spite of DC grounding, negative will not be available here because there is a open contact here. If actual relay operates, actual fault occurred, then only this contact gets closed and negative will be available. So this is the bus differential modification in 220 kV switcher MTPS, major thermal power station. This is the modified block, and we have there is control room instruction was also given, that is the instruction manual, how to work and how to operate, and CT secondary terminals related issues. So second one, this is the bus differential modification and DC grounding removal case studies. Right? Based on this case studies, we have obtained that DC system, which is the heart of the protection system, shall always be in ideal condition, that is the positive and negative should be 50-50 for protection system. And second one, if any bus differential, I am given the example of bus differential protection, we have modified for any case, any protection system, if such thing occurs, then we have to adopt the process of any contact block which isolates the negative path, so that in spite of DC grounding for some time, because if DC grounding already occur, if happens, then we have to rectify this DC grounding. So in that portion also, from the faulty time to the restoration, in that time also, we have to prevent any failure. That's why the negative block, any protection contact shall be provided in positive side as well as negative side, any circuit, for any circuit. So this is the outcome of the case studies. Now coming to the dual earthing of CT circuiting, during this is the current transformer, this is the current transformer, this is the current transformer, this is the two main, the main bus 1, main bus 2 and transformer. This is the two main and one transformer bus scheme. So this is the current transformer. Normally, normal condition of transformer, current transformer circuit is a protection circuit is grounding either at field end, this is the field end and this is the relay end. This is the LBB relay, local breaker backup relay. This is the end. Normally at any one end, grounding should be there. During the testing of the relay, there was done another grounding. So during the testing, induction voltage created, and due to this inductant voltage, current flows to the to this part through relay, and through the grounding path it continues its flow path, and due to that LVB relay operates with other condition also satisfied. For LVB relay there are two conditions. One is the current, and lockout relay also there. Lockout relay was not resetted. Lockout was in operated condition for this breaker. So LVB relay, here I want to discuss one thing. There is LVB relay. I am saying this word several times. This is local breaker backup relay, or it is called 50 BF or breaker failure relay. So when it operates, when this breaker is dedicated for this way. Suppose if any fault occurs at this end, so this breaker should trip to isolate this faulty part. If this breaker stuck or not gets inoperative, then this fault will not be clear, and this fault will propagate to this system, and this all system equipment will be damaged or will be affected by this fault. To minimize or to isolate this faulty part, so this protection operates this LVB relay, and this LVB relay contacts operates all other ways, operates all other breaker from on to off condition. That is, trip command send this relay sends trip command to all other breaker already connected to this bus. Suppose it is connected, two isolator is there at a time, only one isolator is connected. So it is getting power from this main bus 1. Main bus 1 is energized. There are another bus, main bus 1. There is another breaker or feeder also there. 1, feeder 2, feeder 3. There all will be similar breaker like this. So LVB relay sends trip command to other breaker, because this breaker is inoperative. Send command to other breaker, and other breaker gets tripped. If all other breaker gets tripped, then this bus will dead. This bus will not get any energy, any power from any sources. So this fault will get isolated. So to minimize, to isolate this fault, if any breaker, it is dedicated breaker, gets inoperative or stuck, then this LVB relay sends trip command to all other breaker connected to that bus. That is LVB relay. So for CT secondary, for dual earthing in CT circuit during testing, so this occurs. Then we have what we have done. This we have adopted the best practice that we are not grounding at this end, only sorting. So only one single ground will not hamper any system. So this is the practice we have obtained from this type of tripping. So another case study is the short circuit test, short circuit rating of current transformer. So for major thermal power station, 220 kV CTs are having 26.3 kiloampere short circuit rating. So for CT measurement, there are two types. One is protection CT, and another is metering CT. For protection CT, the BH curve is this is the excitation curve. For protection CT, the saturation is in higher zone, and for metering CT, the saturation level is at the level of full load current, so that it cannot damage any meter. And for protection CT, this line, straight line, is the main point. But if any system incorporates number of lines more than its capacity, then the fault level of the system increases. Suppose this is the bus system, 2 main and 1 transformer bus scheme. This is the SLD of major thermal power station. During the time of main bus 1 and main bus 2, this one is the initial condition. After that, there was added of main bus 3, main bus 4. So due to addition of this base, the fault level of the system increases. So when any fault occurs, this is the Gola line, this is the Gola 2, this is the Durgapur line. If any fault occurs at this point, this fault current increased in the level of 30 to 35 kiloampere. So, but we had the short time rating of 26.3 kiloampere. So at that time, what it done, if 26 excitation current increases, but this saturation, it enters into the saturation zone. After 26.3, it enters into saturation zone. So the secondary will not reflect the extra current, high current, and it will not operate own protection. Then the bus differential operate, then it will operate to bus differential protection, and it will trip the total system and failure total system. So after that, CT replaced for the system to ensure the non-saturation of CT for high fault level. Now, better maintenance practices adopted in switched, that is thermography. Based on the above, different types of maintenance practices adopted, that is the regular vital equipment like CT, circuit breaker, transformer, bushing, LA, scanning is being done. Thermography on monthly basis, each and every equipment is being done. Ensure reliability and reduce unwanted outage due to overheating failure. Thermography, that is done. SF6 monitoring and handling, that is the SF6. This is the breaker. For breaker, there are two types of division. One is based on mechanism, operating mechanism, and another is based on arc quenching medium. So for the 220, for 33 and above, normally we use SF6 gas. But at present, up to 145 kV, there are vacuum breaker also there, and this is the best solution, better solution for vacuum breaker. For 220 kV above, there is still SF6 is used. So SF6 we have to monitoring properly. This is the sample of SF6 monitoring. This is the fail. What should be the SF6 analysis? SO2 level, whether SF6 N2 level should be there normal, but moisture is greater than that. Moisture is dependent on the dew point. Whether for the dew point, normal initial condition dew point should be minus 36 degree and above. So this one moisture is 39 degree based on dew point. So it passed. So minimum 36 minus 36. So based on this test, that is the SF6 analyzer make of WICA. So we can consider that SF6 is okay or not. So SF6 monitoring, handling, quality, and thermography, and also testing of equipment on schedule basis. Different remedial action was taken based on the condition, LA monitoring, etc. Best practice based on the LA monitoring. For LA monitoring, we are occurring the leakage current monitoring, IR value, PI value, etc. We are maintaining. For trend delta test of CT, bushing, transformer on yearly basis. Trend based on the trends monitor and action taken accordingly. And for transformer, there are DGA test, online moisture test are done accordingly on schedule basis. So future planning for DC system, we have already what we have discussed. For that one, we have planned another thing that if DC grounding occurs, then based on the AI, we can consider this flowchart and based on AI, so that automatically it will tell us through our message that fault occurred, we have to take action. So now coming to another case of transformer. So this is the case of GT3 occurred in 2022. During the fault in the stator, that is the protection system occurred is the 100% ACF, 100% stator at fault, and 95% stator at fault. These two type of fault, two type of protection acted. This means there is earth fault in the system. So due to that, this is the picture of LV bushing. That fault leads to the failure or bursting of LV bushing. So this LV bushing bursted due to the improper monitoring of the system, transformer bushing, and also the stator. This is the case one, that is the failure in transformer bushing. This is the generator transformer bushing. This failure in this condition, and it tripped the unit instantly, and the interruption was there for a long time. So if any fault occurs in GT, there is no option other than interruption. Reliability and restoration period, it may goes to 7 days to 1 month or 1 year. So that is the non-availability of unit. Second one is the UAT 1B. 1B also there is the Buchholz operation. Transformer one is the most protection, most important protection of transformer is Buchholz protection. Buchholz protection operates when any fault occurs inside the transformer, and it creates gases, and it creates oxidation with the transformer oil, and create the diesel gases of transformer, and these gases flows to the top portion of the transformer through the pipeline to the conservator tank, and there is the Buchholz relay is placed in between conservator tank and transformer tank. So this gas is trapped in the Buchholz relay, and Buchholz relay operate and immediately trip the unit as well as the UAT transformer. UAT means unit auxiliary transformer or thermal power plant. Testing was done, that is the gases collected, there is diesel gases collected, and testing was done. So based on that, the transformer was not usable for a long period up to the 2006 to 2011. After that, it was again put into service. Another case study was failure of 150 MVA auto transformer. That is also happened in Borjoda substation. There is also HV side bushing failure occurred, and bursting was there, and all the consumer